So hello everyone, this is lecture 16 for the classical physics. In the last lecture I have given you this question to you and I hope you tried to solve this, and let me give you the solution. So this was our object, this was thrown from here and it is grazes to the ground at this point. So first we will consider the angular momentum conserved at this point and this point. So here it will be mvr, so mv will be r plus h, and here it will be mv capital R. So this radius is r, so r plus h here, and here it is r. So we'll write this equation as this: mv r plus h equal to mv1 r. So from here you can find the v1. So v1 is at this point. So now you have v1 in terms of v. Next you will do the conservation of energy. So energy at this, the potential energy and the kinetic energy will be this minus gmm over r plus half mv1 square. So this is at the grazing point actually. At this point will be minus gmm over r plus half mv1 square. At this point will be half m1, half mv square plus minus gmm over r plus h. So this will be your expression. Now you just take this expression to this side, and in place of v1 we will write this v, and then we will solve it for the v. So here is the expression. So you can see I just simplified this equation. Okay, and the last you will get this v will be under root 2 gmr over r plus h plus 2r. So this will be your answer. So today we will end the gravitation. Okay, so let's see the last thing in the gravitation, that is gravitational self energy. So there are sometimes questions asked from this topic also. So what is gravitational self energy? It is the work done in assembling the body by bringing all its constituent particles from infinity to the given shape and size against gravitational force between these particles. So the amount of work is done to maintain a shape or to make a shape by small particles with small masses. So the amount of energy stored is called the gravitational self energy. So let's try to find for different type of things. First let's take a hollow sphere or a cell and see gravitational self energy of a cell. So let's consider there is we are making a shell with radius r. So we put some mass small m at an intermediate stage. We take this stage that is intermediate. So mass is small m now, and now we are bringing a small particle, means we are bringing all the particles to this distance capital R, and by putting small masses we will make a bigger means large capital M mass. So at intermediate stage, when there is only small m mass over this spherical cell and we are bringing small dm mass over it again, so at infinity potential will be 0, and at surface we know potential is nothing but minus gm over r. This is small m. Okay, so bringing this point to this point, the amount of work done will be the work done against this potential. So potential multiply dm. So the work done in bringing small mass dm from infinity to r is dw will be dm multiplied potential. So potential at this point is nothing but vs minus v infinity. So at v infinity it is 0 and vs is this minus gm over r. So this will be your work done to bring a small dm mass from infinity to this point at an intermediate stage where mass of this cell is small m. So this is dw. Now we can integrate this whole integral, means this is a small work done. Now from very 0 to capital M mass we can integrate this whole thing. Okay, then we'll get the whole amount of work done to bring or make this hollow sphere complete from a 0 to capital M mass. So total work done in creating the spherical cell will be W will be integration of dw, and this g and r is constant, we will take them out. So this m will be integrated from 0 to capital M. So that is what we are increasing by small dm mass from 0 to capital M. That's why we are integrating this. So integrating this will give you this. So this is your total amount of energy stored in the spherical cell to make this arrangement. Okay, so this is called the gravitational self energy for a spherical cell or hollow sphere. We denote it by US. Okay, now let's see gravitational self energy for a solid sphere. Now this is our solid sphere with capital M mass and radius r. To make this sphere, let's consider our intermediate stage again, where this small sphere is there, whose mass is small m, and we are bringing a small dm mass and making a very thin layer over it, over this m mass, and that's how we are doing this, means dm mass and again dm, that will make this whole complete sphere. So that's how we are processing. So we will consider this case and we'll integrate this to the from 0 to capital M. Okay, so that's how we'll proceed. So this small sphere has x radius, and we bring this dm mass, then that will make a layer with dx width and mass of dm. So the amount of work done to bring this dm mass to this surface is the potential at this point multiplied dm. So potential at this point of the surface of the solid sphere is nothing but minus gm over x. We know this, we already proved this expression. So the work done will be the dm multiply the potential, so it will be minus gm over x. So this will be our work done to bring this charge and this mass and make this. Okay, now we need to find the value of dm and m in terms of m and r. So how we can do that? So let's consider the mass volume density. So this is capital M divided by this total volume. So this is our density, this is our expression for density. Now the dm or the small m mass is nothing but density multiply volume will give you mass. So density is this, and volume is nothing but 4/3 pi r cube, here r is x. So this will give you small m. Now to find the dm, how you can find the dm? It will be again volume into density. So volume of this small layer is this area multiply this width will give you the volume. So area of this hollow sphere is 4 pi r square. So 4 pi x square will give you the area, multiply this width will give you the volume of this small layer. Okay, so 4 pi x square dx multiply density, this will give you dm, this mass. Okay, this is volume, this is density, this is mass. Now you have value of m, you have value of dm. Substitute them here and integrate dw to make it w, and integrate with 0 to m, or it is in the terms of dx. So we are increasing layer by layer by dx, this dm giving dx layer. So we can integrate dx from 0 to capital R. Okay, so just substitute these expressions in this expression, so we'll get this, and now we have dx here. So after solving this, many terms will cancel out, we will get this expression. And now this is the expression for dw, we will integrate dw, and it will integrate x from 0 to r, x for dx. So this will be x5 over 5 and it will be r5 over 5. So r5 will give us r here in the denominator. So we will get minus 3/5 gm square over r as your gravitational self energy for a solid sphere. So this amount of work done is required to make a solid sphere of radius r and capital M. Okay, so this is the amount of potential energy stored. Now let's see some questions. Two planets P1 and P2 having masses m1 and m2 revolve around the sun in elliptical orbit with time period t1 and t2 respectively. Minimum and maximum distance of P1 from sun are r and 3r respectively, whereas for planet P2 these are 2r and 4r respectively. Assuming m1 and m2 are much smaller than the mass of the sun, the magnitude of t2 over t1 is. So there are two planets revolving around the sun. So we have the different radius and they are moving, means the minimum and the maximum distance of the ellipse. So if there is ellipse and you have the minimum and the maximum distance, then sum of these distances divided by 2 will give you the semi-major axis. So for planet P1 it will be 3r plus r, 4r divided by 2 it will give you a equal to 2r. For P2 it will be 6r divided by 2, it will give you 3r. So and you know the relation t square is proportional to a cube. So t2 over t1 will be this, means just substitute the value t2 over t1 equal to a2 over a1, and you already find it the a2 and a1. So you will get this expression for this t2 over t1. Now a satellite moves around a planet in a circular orbit at a distance r from its center. Time period of revolution is t. If the same satellite taken to 4r around the same planet, then time period will be. So again it's a satellite moving around a planet. So first it is at distance r and time period t. Now it is taken to the 4r, and now time period you need to find. So you will use the same relation t2 over r2 equal to t1 over r1. So that's how T2 over R2 will be T2 over R1, or you can say that T2 over T1 equal to R2 over R1. So you can find the value of the time period. Now let's see one more question. First, see this figure. It is an equilateral triangle. 3 masses are given, 3m here, m here, and 2m here. So let's see the question. At an instant zone, at a particular instant, 3 point masses m, 2m, and 3m rest on a horizontal surface and are at the vertices of an equilateral triangle of unit side length. Assuming side length is unit, okay. Assuming that capital G is the gravitational constant and magnitude and direction of the torque on 3m about the point O at the instant is. So we need to find the torque on this mass 3m, okay, at this instant, and this is the condition. So there are many ways to solve this, so I will give you the shortest trick or the shortest way. So see, you need to remember the torque formula, that is R cross F. So if here is the origin, then the R vector will be in this direction, and force due to this one is in this direction, force due to this will be in this direction. So this is F1, this is F2. Now the component of F1 in this side and F2 in this side. So total force in this direction will give you torque 0, because this angle is pi, and cross product will give you 0. So you have to take these component, F2 sine 30 and F1 sine 30, and these are in the opposite directions. So find the magnitude and subtract them and just multiply them with R. So you will get the value of torque. So see, you can do this like this also. Or there is a second way, means total torque will be R cross F, means direction will be perpendicular upside, and for this one R cross F will give you direction downside to the inside the paper. So just find the magnitude. It will be R cross F, means RF sine this angle will be 150 because this is 30. So we will take these two, RF sine 150 minus RF2 sine 50. Now we take a negative because the second one is in opposite direction inside the paper. So we will take R sine 150 outside. F1 minus F2 will be, so F1 is nothing but G mm over R square. R is 1, so we'll get G 3m multiply m, and second again it is G 3m multiply 2m. So this will give you 3 to 6 minus 3 minus 3 gm square. So this will be your magnitude, and sine 150 will be pi minus 30 will give you sine 30 will be 1 upon 2, so root 3 upon 4 here, and root 3 gm square from this side. So you will get this, and this will be negative, so it will showing that direction of this torque will be inside the paper. Okay, so that's how you can solve this question. Now let's see one more question. There are 3 planets in circular orbit around a star at distances a, 4a and 9a. At time t equal to t naught, the star and 3 planets are in a straight line. The period of revolution of the closest planet is t. How long after t naught will they be in the straight line? So question is like you have sun or any star, and there is these 3 orbits around it. The planets are orbiting. So at a particular instant, these all are in same line. Okay, and we know the time period of first one, so we can find the second one and third one using the radius. Okay, using the relation we already know, t square equal to r cube. And when you get the time period for all, then at a particular instant t, so you will get time period for different one will be this. This is a k constant. This is nothing but 3 by 2 will give you 1 by 2 will give you a square. So t square r cube, we use that relation to find this relation. So t1 is t given, t2 will be 8t, and t3 will be 27t. Now see the LCM of these all 3 will give you the time at which they will come again at the same position. Okay, so this is the lowest common multiple, that's why we call it, because at that time they will be again in the same position. So LCM of these will give you 2160. So this will be your answer. After this time they will be again in the same line. A body of mass 1 kg is moving under a central force in an elliptical orbit with semi-major axis 1000 meter and semi-minor axis 100 meter. So A and B are given of an ellipse. This is an ellipse. So this is B, this is A, and this A is semi-major axis, this B is semi-minor axis, and orbital angular momentum is given 100 kg meter square per second. We need to find the time period of the motion of the bodies. So you know, when this A and B are given, use this relation. Means we know about the aerial velocity. We already proved this, that this is equal to L upon 2m. This is angular momentum, this is mass. So aerial velocity will be total area divided by time period. So area of ellipse will be pi AB divided by t, where AB are semi-major and the semi-minor axis. So these values are given. So use the relation, t will be 2ma divided by L. So A will be pi AB divided by L. L is given, M is given, 2 is, you know, and pi is 3.14. A and B are 1000 and 100. So you will get your answer. So that's it. We have completed the gravitation. We discussed all kind of question can be asked from this portion. From the next lecture, we will start the Lagrangian. Thank you everyone.